Hello, class. Today, we're going to be talking about similar triangles, and this specific part is about the proportionality constant. The proportionality constant is, in a way, okay, this might seem weird to say, but it's what you multiply a triangle by to get another triangle. What I mean by that is you can take a length, and let's say that's a length of 2, could be 2 feet, could be, 2 meters, whatever. And you can multiply that length by 2 to get another length, and that length would be 4. So the same concept applies to triangles. You can take some triangle, some equilateral triangle, let's say every side is 2, multiply that whole triangle by a factor of 2, and get an equilateral triangle. I know I'm going off the screen, but trying to make a point. You can multiply a triangle by 2 and get another triangle that's the same triangle, but has all lengths of 4. So this proportionality constant is basically telling you what you're multiplying one triangle by to get another triangle. And the way you find this proportionality constant is you just take the ratio of the two sides, because you can think of each side as being that length of 2 being multiplied to get a length of 4. And the way you would see what I multiplied these lengths by, well, you would just take 4 over 2, right? And that would tell you that I multiplied it by 2. So we're going to do the same thing here. We take the bigger length A and divide it by the smaller length x. And these are the same sides of the triangle, which is an important part of it. You can't divide a by z to get the proportionality constant. You have to divide the same sides. This proportionality constant is always going to be greater than or equal to 1 if you divide the bigger side by the smaller side. So that's another thing. If you divide x by a, you're going to get something that's less than 1. Because in order to get to x from a, just like in order to get from 4 to 2, you have to multiply by a half, right? So if I did 2 over 4, then I would get a half, which tells me I would have to multiply a side of 4 by a half to get a side of 2. So you always want to make sure that you're putting the biggest side on top. So biggest over smallest. You're always going to want to do that in order to get the proportionality constant. And again, this is going to be another asset in finding out the lengths of sides when we talk about similar triangles. So let's pause this again. I'll give you some numbers and hopefully that'll clear up any ambiguity. Here we have another example. And this example is a little bit different than the ones you've seen in a few regards. First, I want to point out that I made this lettering scheme a lot different. It's not A, B, C, X, Y, Z. It's something more random, if you will. And it's good that the book, because I got this example from the book, did this because your labeling system doesn't have to be something that necessarily is easy to decipher. They're just letters, they're just labeling something. It doesn't mean anything. So you do have to be careful that when you're trying to solve similar triangles, you're putting the right sides with the right matching sides, if that makes sense. Because also one thing that the book will do and my math lab will do is it will rotate one triangle a certain degree. So even if two sides may look similar, you have to make sure that you're looking at the angles and making sure that the sides are the side that you think they are. So that's just one cautionary note. Um, and then the other way that this is different is that we don't have any ratios that we can make in order to solve for these two missing sides, YR and QM. So we're going to try to solve for these without using the method of ratios. And the way that we're going to do that is we're going to look at two sides that we do have, 3 and square root of 5. So these are similar sides, And what we can do is find the proportionality constant between these two similar triangles. So again, it might not be obvious, but square root of 5 is it greater than 3? No, I actually think I think 3 is greater than square root 5. Yeah, 3 is greater than square root 5. So what we have is our proportionality constant k is going to be equal to 3 over square root 5. So I got this by taking BR, the length BR, and putting it over side MT. Okay. And again, I made sure to put the larger one on top and the smaller one on bottom. This is so that way k is greater than or equal to 1. Okay, now what can we do with this k? Well, we know that the other sides, QM and YB, are, oh, I'm sorry. I just realized the reason why I thought 3 was smaller for a second was because I put it on the smaller triangle. So I'm sorry if that confuses you. Actually, let me change that real quick. 1 second. Okay, now our graph matches our numbers. Our triangles match our numbers. So this ratio now is going to be MT over BR. And one other thing, so we're looking for YB, not YR. So this is, we're solving for YB and QT. Sorry again if that caused any confusion, guys. So here we have our proportionality constant, which we got for putting the larger side over the smaller side, which is MT over BR. And we want to solve for, let's do QT first. So QT, we can make a ratio with this side and YR because they are the same sides of two different similar triangles. And we know YR, right? QT over 4. Now again, because we're comparing these two sides, this side and this side, and we're putting that into a ratio, that should be equal to K. And K is equal to 3 over square root 5. So then what we're going to do is we're going to multiply both sides of this equation, QT over 4 and 3 over square root of 5 by 4. And what we'll get is we'll have QT equals 3 over 5, square root 5 times 4, which is equal to 12 over square root 5. Check my notes, make sure that's right. QT equals 12 over square root 5. Yeah. So this is going to be one of our sides. And again, I'm going to pause the video, rewrite this, and solve for the other side. Okay, now that we solve for QT, we want to solve for YB. So YB is over here, and that can be compared to this side, which is square root 11, or QM. So QM is going to go on top. So QM over YB is equal to, again, K, right? Because we're comparing two sides, and that's going to be equal to the proportionality constant. So QM is something we know, which is square root of 11 over YB, which is what we're trying to solve for. That's going to be equal to 3 over square root of 5. Okay. Then what we do is what we did last time. I'm just gonna, I want to move this, but I might just rewrite it because I'm running out of room. So what we're going to do is we're going to multiply this YB to the other side, and we'll get square root of 11 is equal to 3 over square root of 5 times YB. And then we can multiply by square root of 5 over 3, and we'll get YB is equal to square root of 55 over 3. Okay, that is our second length. I hope you guys didn't get confused by this math. I know I had to kind of cram it into a small area, but I'm at 10 minutes now. So just comment down below or shoot me an email if you have any questions about this. This is going to be it for similar triangles. Tomorrow, again, we'll be talking about special right triangles, and then we'll be getting into trig functions. So I hope this made sense to you guys. I hope y'all having a good one, and I'll see you next time.